Welcome to week 6. We're still in our physics unit. Today we're going to talk about net force and balanced and unbalanced forces. First off, with Zoom, make sure you're all authenticated. If not, you're not going to be able to log into class, so there's some information here. If you're struggling, same stuff you've gotten before, but just right where you might need it. Okay, you'll see we're going to do some practice, and then you can check yourself. You'll have a maze and a brain pop to do. But first, we have notes to put in. So we'll open up my science notebook, which I already have open, and we're going to put in a page of notes. I'm going to show it in a little different way so it's bigger, but you'll copy these notes in, and then we'll set up our page to do our net force practice. Okay, so one thing at a time. Okay, so make sure you put your page number and date. Your title is net force. Okay, you've heard these words before, but not necessarily in the same context. So from elementary, you know that a force is a push or a pull, right? And we measure it. Think of a spring scale. In your everyday life, when you step on the scale to see how much you weigh, that is actually measuring your weight, not just your mass. And your weight is your mass times the pull of gravity. And that is actually can be measured in newtons. But remember, we do customary, so you have it in pounds, right? But it's named after Sir Isaac, and notice the unit is a capital N, right? No naked numbers. So remember to always put the unit after the numbers, okay? The word net, when you start learning about paychecks and taxes, you'll see there's the amount of money that you thought you were going to have on your paycheck, which is your gross income. Let's say you thought you were going to get $200, okay? But when you get the check, you have the net income. That's after your taxes and all the deductions. So it's what actually goes into your bank account. So it's kind of like the leftovers. Or thinking about a physical net, like to catch fish. You throw it over the side of the boat. You draw out the net. All the water leaks out, and what's left over in the net is the fish. So it's kind of the leftover bit. So the net force is the overall force on an object. Okay? And we say object as a generic thing because object sounds fancier. So when on any of these, if you get confused, substitute in something that makes sense to you. Like if you're a soccer player, think about a soccer ball. If you're into fast cars, think about a fast car. Put it in terms that make sense in your everyday life. All right. So first thing is we need to differentiate between balanced and unbalanced forces. Okay, so when forces are balanced, you're going to have a net force of 0. So the overall, the forces acting on it is going to be 0. This little slash there, we use that a lot of times to differentiate this 0 from an O, like a capital O. Right, so just FYI. Okay, but notice that a balanced force does not change the motion of an object. Okay, there's a lot of misconceptions you could walk away with this, so we need to make sure that we have it completely straight in our head. Okay, changing the motion of an object is called acceleration. And we'll go into this more during this unit, and then you'll see it again in 8th grade and then in high school physics. And most people, when they hear acceleration, they have no problem knowing that means to speed up. Right? Like the gas pedal in the car, the technical term is the accelerator. But acceleration can also mean to slow down. It can be a negative acceleration, sometimes called a deceleration, but it still falls into the same category. The one that people forget about most often is this one where it's changed direction. And remember this triangle, it's the Greek letter delta. Okay, so we talked about that a couple weeks ago, and that is the symbol we use in science for change, right? So it's a lot faster, not that change is a big word, but a lot faster than writing that out. Okay, so to think of this one, think about like fast cars like Fast and the Furious, or when someone drifts, right? They don't change their speed, but instead of going north, now they're going east, right? So all 3 of these are examples of acceleration, which is the change in the motion of an object, okay? You can have a balanced force and be on cruise control, right? So you may not be driving yet. Maybe you've driven like a golf cart or something, but in a car or a truck, a vehicle, have your parents show you where the cruise control is. Because if you're going to go on a long car trip, your feet and your leg get really tired holding the pedal down. And if you're on the highway and you can go 70 miles per hour, you can set the cruise control to help you maintain that speed. So you don't go above 70, you don't go below 70. You can be balanced and be moving, right? Because notice here, none of this said that you're not moving at all. It can be on cruise control. Right, so you're not speeding up, you're not slowing down, you're not changing, but you are still in motion. All right, so those 2 things are probably the biggest misconceptions people have. And once you have that straight in your head, everything kind of falls in place. All right. Now to look at unbalanced compared to balanced, it's pretty much the exact opposite. If balanced forces, the net force equals 0, and unbalanced forces, the net force does not equal 0. That's what that means. It's an equal sign with a slash through it. It means does not equal. Okay, so any other number besides 0 is going to be unbalanced. And these do change the motion of an object. So any of these here, speed up, slow down, change direction, will cause an unbalanced force. So think about, hitting the gas to make it through the yellow light. You would never do that. To slow down, right? Maybe you had to slam on your brakes because someone pulled out in front of you, or to change directions. Maybe you're a stunt driver in an action movie and you're doing that drifting. Okay, so we got to keep those things straight in our head. All right. When we draw these, we're going to keep the drawings pretty simple. I often joke that it is not my skill set, but usually you'll see scientists just do a simple box as the object. All right, it may be a teddy bear, it may be a ride at Fiesta, Texas. It doesn't matter what the object is. Okay, and then in our drawings, our arrows are going to represent forces. So unless they are intentionally trying to show you conceptually with like squatty fat arrows or long skinny arrows, do not rely on the arrow shape. It's kind of like in math. Always look at the measurements, right? But that's what these things are going to represent. Okay. When we're doing this, I'm intentionally giving you easy math because we're not, like I'm not, what is it, second grade when you're doing 3-digit addition and subtraction. That's not my concern. I mean, I am concerned if you can't do that, but our focus is on the concept or the formula. Okay, so we're going to keep the numbers simple so that we're not stressed about the numbers, we're worried about the concept. Okay, so let's say I have an object and I have two forces pulling on it. Maybe this is like a rope and you're playing tug of war at field day. Okay, so you got 500 newtons going to the left. Notice the direction the arrow is pointing. Okay, 450 newtons to the right. Notice they're both going away from the box. They're both exhibiting a pull. All right, but they're going in opposite directions, so they're working against each other. So mathematically, if the forces are in opposite directions, you're going to subtract because they're working against each other. And I know you could do 500 minus 450 in your head, but we're not worried about the numbers, we're worried about the concept. And as simple as this kind of is, you're way more likely to make a mistake if you don't write it out. Okay, there's a couple of different ways you could go wrong. So you set it up, your 400, put the bigger number on top, right? 500 minus 400, but notice what I've added. I have the unit, and I have which direction they're going. So sometimes people will look at the arrows and get a little confused. Look at what direction it's pointing. So this one's moving, the 450 is going to the right, and the 500 is going to the left. So you've written that here. The subtraction part's the easy part, but remember, no naked numbers, so you have to put your unit. And then look to see which one of those was bigger. Like if this was tug of war, which team's going to win? So this one is to the left because the 500 Newton was a larger force. When you write this out, and you see it sometimes, they will refer to the number and the newtons as the magnitude or strength. You've heard the word magnitude with earthquakes. Like the magnitude of the earthquake is like a 5.0 on the Richter scale, right? And you also need the direction, because just knowing the strength without the direction doesn't really tell you a lot. Okay? When we get into the difference between speed and velocity, this will come into play as well. So looking at my net force is 50. 50 does not equal 0, so it is unbalanced because of that. Okay? But maybe instead of a pull, we have a push. Okay? So two different forces, just throwing in some different numbers. So notice they're both going towards the object. All right, so they're pushing in on the object, but they're still going in opposite directions. The 25 is going to the left, the 5 is going to the right. Okay. I can't talk. I totally just messed it up. See, even I, when talking on this, would mess it up. So the 25 is going to the right, and that's why we write it down to double check ourselves. And the 5 is pointing to the left. So simple math, but notice I have my unit. The 25 was the bigger one, right? So it's going to go to the right, and this is also unbalanced. Okay, we'll do some practice where it's balanced so you can see that too. I just wanted you to see a push versus what a pull looks like. And we're keeping it simple with two arrows. Our real life stuff have a lot more things acting on it, right? So we're going to build on this. Now, if the forces are going in the same direction. Think of them as being on the same team. You're going to add them up. All right. So let's say the car stalls out, you ran out of gas, the battery died, whatever, and you and someone else are having to push the car. Okay, so you're both applying, see it's going towards the object. So here, that's a push, right? You're both pushing the car to make it go to wherever you want it to go. But it's a teamwork, right? So you're going to add them together this time, right? Get your total with your unit, and there's only one way for this one to go, okay? But it is unbalanced because it doesn't equal 0. You want that car to move. That's the whole point, okay? It doesn't matter if the arrows are on opposite sides. In this case, this one is pushing, and this one is pulling. So maybe there's a cart and a wagon, and the horse or donkey is pulling on it, but it's stuck in the mud, so the farmer has to get out and help push from behind. Okay, they're still going in the same direction, so they're still working as a team. So you're going to add the numbers together, right? Get your magnitude, get your direction, and that one is also unbalanced. All right, so just think through it common sense. Fill in something you're familiar with your object if things get a little confusing, right? And don't skip writing this part. Because even when I was explaining it to you, body, say the wrong thing. But when you write it out, go back to the picture and double check yourself. Okay. On that next clean page, you'll set up your page to do some practice. Okay, the net force practice. There are, it's just me fighting with the document camera, no big deal. There are 10 problems. So I just folded my page in half, right? And you can go back and put a line there too. I was in a hurry in class, so I didn't. Right? And just kind of number it off. And I'll show you where this goes in just a second. But notice how I've written out the problem. And on this first one, okay, and I'll show you in just a second what it looks like. I ended up with 0. Notice there's no to the left or right in my answer because it's not moving. So if it's not moving, it can't go left or right because it's not moving. So this would be balanced. All right. And then in the second example, and this practice is on Classroom. I'll show you in like 2 seconds. In the second picture, you see 3 arrows. You're like, whoa, that's 3 arrows. We didn't talk about that. It's the same concept, right? These guys are on the same team. So I added them together, right? So 80 newtons plus 20 newtons kind of on the same team equals 100 newtons going towards the right. And then it's countering 100 newtons going to the left, which still gave me a balanced net force, right? So this goes with, let me switch over, in Classroom. Okay, like there's the 2 pages we just went over in my science notebook file, right? But in Classroom, this net force practice, okay, it opens as a PDF. You don't have to write anything on it. Everything I want in your journal, and somebody wrote on mine. So I'll go in and erase that. That's fun. But here, there's the example that we just did in our notebook, right? And that second picture where you added them together, right? So some of them have 2 or 3, but you'll go through and practice on these. And then I have already, once you're done, don't be a cheater. Doesn't do any good to look at my answers. Miss Melody already knows how to do this. I put the key here so you can check yourself after you've finished all 10. Okay. When you've got that done, you will do the net force maze. You'll be using Kami. Notice up here where it says open with Kami, or here, annotate with Kami. If you're not familiar with Kami, there is a video on the stream on Classroom you can watch to help you out. But you're going to start here at the apple tree, and you have 2 options with this net force problem. It's either 41 newtons to the right or 41 newtons to the left, and you'll use the Kami marker to draw on it to work your way through the maze, right? And then you'll turn it in just like you normally would on Classroom. Okay, so work your way through. Just in your science notebook, you can make a page to do the math on it. Okay, don't try to do it in your head, just like we already talked about. Okay, so you'll do your maze, right? And then you've got a quick brain pop. It's just, if you don't remember how, Launchpad, Library Services Brain Pop, most of you are pros at this. It's the forces video and take the quiz. While you're in brain pop, double check that you've actually completed the other science brain pops. Some of you have marked done on Classroom, and when I go in brain pop, it is not done. So I'm going through and looking at those. Don't be that kid, okay? So you will knock that out before I see you again, okay? And remember, you can always come to tutoring. Let's see, let me scroll down. It's on here. Right?